Hello, this is John from caveofprogramming.com. In this tutorial, we're going to take a look at how integers actually are represented in the computer's memory. This lecture is kind of optional if you're following through this C++ tutorial video by video. And if you are, congratulations on getting this far, by the way. So if this subject doesn't interest you, you can definitely live without knowing this. But for those who are interested, I wanted to include this video because it's kind of interesting actually. So I'll tell you the most important bits first, and then if you want to start watching, you can do so without it wrecking your computing career or anything. So I've got a little program here, and I've created a char. So it's a signed char because values are signed by default in C++. And I've set it equal to the maximum value that you can fit in a char, and I've output that value and incremented it. So if we put the maximum value that we can in some primitive type and increment that, C++ won't warn us. It won't give us an error. It won't even give us a warning, I shouldn't think, because it just doesn't check. It trusts you to know what you're doing. So you have to be aware of, roughly at least, the maximum values that you can fit in integer types, especially with the really small types, especially with char, where you can only fit 127 in there. So if we increment 127 and output it again, we actually end up with minus 128, which is actually the most minimum value, the smallest value, or the most negative value, if you like, that you can fit in a signed char. Now you notice that we've got plus 127, but minus 128. And the basic reason for that, we are going to go into it in detail, but the basic reason is that you have to represent the zero in there. So you can think of the positive values as ranging from 0 to 127, although 0 isn't really positive or negative, but we have to represent it in that memory. And the negative values go from minus 1 to 128. So it's basically because the 0 is taking up a space in here, in this sequence, that the maximum positive value is 1 less than you might expect on the basis of the most negative value. And this is the same for all the integer types in C++. I just picked char because it's easy to deal with because it's so small. So how exactly do we represent integers in the computer's memory? Well, first of all, let's have a look at this whole maximum and minimum value thing a bit. So if we imagine that we have, let's imagine that we've got just 3 bits. So let's say 3-bit system, and the most maximum value that you could sign, that you could store in an unsigned 3-bit value. So if we're not interested in negative numbers, just positive ones, the biggest value that you could get in there would be got by setting all of the bits to 1. We can only set each bit to 0 or 1, so if we set them all to 1, then you'd expect that to be the biggest value that you could get in 3 bits. And that equals, in this case, well, this is the least significant bit, we call it, because it represents how many 1s we've got, either 0 or 1. This is the most significant bit, which represents, in this case, how many 4s we've got, either 0 4s or 1 4. So this is 1 plus 1 times 2 plus 1 times 4. So that's 4 plus 2 plus 1, which is 7. And that actually equals 2. It equals 2 to the power of 3. Yeah, that's right, 2 to the power of 3. So 2 times 2 times 2, negative 1. So that's the same as, so to the power of just basically means how many times you multiply the number by itself. So 2 to the power of 3 is 2 times 2 times 2, 3 times over, which equals 8. We subtract 1, we get 7. So that's how you can calculate the maximum unsigned value for any particular type if you know how many bits it uses. So if we've got 8 bits, so 1, 2, 3, 4, 5, 6, 7, 8, that's the maximum value you can store in a byte, for example, an unsigned char. that's going to be equal to 2 to the power of 8 minus 1. And 2 to the power of 8 is 256, so minus 1, we get 255. Now, what about if you want to have signed values in there? Well, one thing that you might imagine doing is you could say, okay, well, we'll keep the most significant bit, for example, to represent the sign. So we could say, okay, let's say that a 0 for the most significant bit means that it's a positive number, and a 1, which looks a bit like a minus sign turned on its edge, we could say that means it's negative. So any number that starts with 0, we say it's positive. Any number that starts with 1, we say it's negative. So it's just a sign bit, and the rest of it is the actual number. If we did that, we'd have one less bit to represent the actual number itself. So we could imagine in such a system that the maximum value we could store, let's say in 3 bits, would be 2 to the power of 2 minus 1, which would just be 3. Or the maximum value that we could store in 8 bits, if it's going to be signed and we need to keep 1 bit for the sign, is now going to be 2 to the power of 7 here, which is 128 minus 1, which will be 127. But as we saw, in fact, the maximum value that we can store in this chart it is 127, but we're managing somehow to get to minus 128 with the most negative value. And that's to do with the way the number is actually stored. So let's have a look and think about this a bit more carefully. Let's keep with this system. The most obvious thing to do is that we say, okay, the most significant bit, this one, is the sign. So therefore 000, that's 0 in decimal. 001, which gives us 1. 010, that's 2. 011, that's 3. If we add 1 to that, we get 100. So we're saying this is negative now because it's got a 1 here. So now we'd have to say that this equals minus 0. And then we go to 101, which we could say equals minus 1. 110 equals minus 2, and 111 equals minus 3. So the idea is that you just look at the bits after the first one, and that's the number, and then the first bit is just a sign. That's the most obvious thing that you could do. But the problem is, this system, which isn't used by any computer that I've heard of, this system, it doesn't let you do arithmetic easily at all. So let's imagine that we want to add up, let's say 1 and minus 1. Let's try that. So 001 is 1, and add to it minus 1, which is 101. I'll put zeros for the answer to start with. So this is 1, and we want to add negative 1 equals. Now, binary arithmetic works the same as decimal arithmetic or hexadecimal or whatever you like, but we're most familiar with decimal. If you've got like 1 plus 1 here, we have to add up the rightmost column first. That's like adding 9 and 1 in the decimal system. The answer is 0, and you have to carry a 1. So this gives us 0 in this column, carry the 1. So 0 plus the carried 1 is 1. And then for this column, 0 plus 1 is 1. And what's this equal to? 110, it's minus 2. So we should have got 0. So plus 1 added to minus 1 should be 0, but we've got the wrong answer. So this system is rubbish. And that's why it's not used anywhere. But we can tweak it a bit. If we tweak it a little bit, we can make we can make arithmetic a lot more easy to do in this system. So it's a system called ones complement, which again isn't used in many modern computers, but it's a much better system. So in ones complement, we keep this almost the same as it currently is, but we say that this, what would be the most positive value if it was unsigned, we're going to say that that equals minus 0. And then we're going to make this minus 1, this is going to be minus 2, this is going to be minus 3. So we've got still the negative numbers have a 1 for the most significant bit. Positive numbers have a 0 for the most significant bit. We've just moved the negative numbers around a bit, put them in different places. And we've got a minus 0 here as well. But we had a minus 0 to start with anyway, even in this naive system. Now things work out a lot better. Let's try this. So if we add 1, 0, 0, 1, which is 1, plus minus 1, 1, 1, 0, which is minus 1, equals, let's do that. So 1 plus 1 is 1, 0 plus 1 is 1, 0 plus 1 is 1. It gives us 1, 1, 1, which equals minus 0, which equals 0. So that's the right answer. So 1's complement is a system of storing signed numbers in some bits that allows you to do arithmetic much more easily. Now there is a bit of a complication sometimes, because let's take a look at what happens if you add, let's say, 0, 1, 1, which is 3, to minus 2, 1, 0, 1. Let's try that. So we're going to add 3 to minus 2, and of course we expect to get 1. I'm going to put a 0 actually at the beginning of these. So of course, as with decimal, you can put a 0 at the beginning of a number and it doesn't make any difference to it. Like 007 still means 7, in a decimal system, so we can do that. Let's try that. So 1 plus 1, well, that gives us 0 and we have to carry the 1. 1 plus 0 plus the carried 1 again gives us 0 and we have to carry the 1. 0 plus 1 plus the carried 1 again gives 0 and carry the 1. And now we've got to put a 1 there. Now there's a rule here. This is the wrong answer, clearly. But there's a rule that we can apply to fix that, which is that if we get an overflow bit on the left here, we have to add it to the right here. So let's do that. Add overflow bit to right. So we take that off there and we add it here. And so that would be 0, 0, 0 here. 0, 0, 0 plus 1 equals 0, 0, 1. And then we get 0, 0, 1. It's the right answer, because 3 added to minus 2 is 1, and 0, 0, 1, of course, is 1. So if we look at this 1's complement system, it works. It works fine, but we've got, two complications at least, and we haven't looked at multiplication or subtraction or whatever, but I believe that they, as far as I know, they work really well in this system. But the difficulty is that, firstly, we've got 2 representations of 0, so we've wasted kind of one place in the system by representing 0 twice when we could have stuffed another number in there. Another deficiency of it is that we've got to do this extra thing of adding the overflow bit. If we get an overflow like that, we've got to add it on to the right hand, to the least significant bit, in order to get the right answer, and only then does it actually work. And that's why we don't use 1's complement in modern desktop computers. What we use is a system called 2's complement. So let's take a look at 2's complement. I'm going to copy this table because most of it's the same. Let's type this out here. Now 2's complement, so these numbers are all the same, 0, 1, 2, 3. Whoops. So 0, 1, 2, 3. But we say that 1, 1, 1, that's going to be equal to minus 1. And then we're going to number backwards from there. So again, any negative number starts with a 1. Remember, we're just using 3 bits here for convenience, but it's the same idea in 8 bits. Any number that starts with a 0 is going to be positive. And you can see that in this system, the most negative value is actually 1 less than negative of the most positive value, if you see what I mean. So we can go up to 3 for the positive values, but we can go down to minus 4. That's what we see here. We see that we're going up to 127, but we can go down to minus 128. So that's because the computer is actually using this system that I'm about to show you here, 2's complement. Now the advantage of doing this, well, another advantage is that we've only got 1 0 in here, so we haven't kind of wasted a place. But also it turns out that arithmetic is actually easier to do than with 1's complement. So let's try, for example, we'll start with, let's try adding 2 to minus 2, 110. Let's try that. What we get is, we should get 0. So if we add 0 and 0, we get 0. 1 plus 1 is 0 and carry the 1, just like adding 9 and 1 in decimal. 0 plus 1 plus the carried 1 gives us 0 when we carry the 1 again. So we end up with 1 overflowing. But the difference here is that instead of adding the 1, the overflowed bit, the overflowed most significant bit, instead of adding that to the least significant bit, like with 1's complement, all we have to do is discard the overflow bit, and we get to 0, 0, 0, which is the right answer. So we still have a funny thing going on with the bits, but all we have to do is ignore them, so we don't have to add them anywhere. So it's easier. Addition is easier than in 1's complement. I'm not going to get into subtraction or division or multiplication, but apparently they're also very easy to do in 2's complement. Let's take another example just for fun. So if we take, I don't know, let's take 3. No, let's take 1 or 2. I'll start with 2. Okay, let's do 2 and minus 3, which should give us minus 1. So this is 2, and let's add minus 3. 1, 0, 1, negative 3. Then we get from that 1, 1, 1. It's quite easy to see the answer. We're just adding 1s and 0s in each case. And 1, 1, 1 is minus 1. Right answer. So there we go. And yeah, adding 2 positive numbers or adding 2 negative numbers, it works just the same. The only thing you have to bear in mind is that if you get an answer that's too big to fit in your type, then you are going to get an overflow. It's not going to fit in 3 bits or 8 bits or whatever. But this system, 2's complement, is the way that we represent numbers in the computer's memory, because it doesn't waste any values. There's only 1 0, and it makes arithmetic really natural to do. We just have to discard some overflow bits. Okay, so that's it for this tutorial. My plan now for this course is that there's only one more thing that I can think of at the moment that is really pressing to fit in a beginner's course on C++. That's static variables. So we're going to take a look at that probably in the next tutorial. And after that, I've developed a rather nice plasma explosion simulation program, and I'm going to show you how to make that in the rest of this beginner's tutorial. So that's it for this time, and until next time, happy coding.